Welcome to the training for Mechanical Science Fundamentals, Cooling Towers. The average time to complete this training is estimated to be 15 minutes. After you have completed this portion of training, you will be directed to the next training lesson in the series for further instructions. These are the objectives for this course. The purpose of a cooling tower is to provide effective cooling while minimizing the thermal pollution of natural heat sinks and allowing the reuse of the cooling water. Before the development of cooling towers, we used natural heat sinks like rivers, lakes, and ponds to supply cooling for industrial facilities. This often resulted in thermal pollution, increased temperatures of these water supplies. The development of the cooling tower gave industry an environmentally friendly alternate source of cooling water. Recall from heat transfer that as liquid evaporates, it takes the thermal energy for this latent heat of vaporization away from the remaining liquid. This evaporative cooling process is used in cooling towers. Hot water from the process is distributed across a pad or baffles to spread the water out over a large surface area. As the water filters down the pad or baffles, cool dry air is moved across it by a fan. Moving air across the water increases the evaporation rate, similar to fanning yourself on a hot day. The air moving across it takes away the hot, evaporated water vapor, removing thermal energy and cooling the remaining liquid. The cooled water collects in a reservoir after leaving the pad where it is pumped back to the system for more cooling. Evaporative cooling relies on three physical processes. The temperature must be above the dew point. The dew point is where the air is saturated with water vapor. The dew point is based on the relative humidity, amount of water vapor in the air for a given temperature. The higher the humidity, the less effective the cooling tower will be at reducing temperatures. The latent heat of evaporation is supplied to the vapor from the sensible heat of the remaining liquid. Recall that latent heat is used for a phase change. The thermal energy used for evaporation comes from the remaining liquid. The decreased thermal energy of the liquid results in a lower liquid temperature. This is a decrease in sensible heat causing a decrease in temperature. There are three primary types of cooling towers based on how airflow through the tower is provided. The first is a forced draft, where a fan is on the inlet and blows air through the evaporator pad or baffles. The second is the induced draft, where a fan is on the outlet and draws air in and across the evaporative pads or baffles. The third is by natural convection, where airflow is provided by natural circulation caused by temperature differences. Using the concept, hot air rises. For the induced draft cooling tower, hot water from the system flows into the distributor, which distributes the hot water across the baffles. The hot water flows down across the baffles due to gravity. Air is drawn from the outside across the baffles by a fan on the outlet of the flow path. The air flowing across the baffles carries away the latent heat of vaporization from the remaining liquid that gives up its sensible heat, causing a decrease in temperature. The cooled water drains out of the baffles into the cold water sump, where it is pumped back to the system for further cooling. The hot moist air is drawn out by the fan on top of the tower. Hot water from the facility process is dispersed over baffles. Baffles cause an increased surface area and maximize the contact between the water and the air. An electric motor-driven fan at the top of the tower draws air up through the baffles. The water works its way down through the baffles and the cooled water is collected in the basin at the bottom of the tower. Forced draft cooling towers are very similar to induced draft cooling towers. They use the same evaporative cooling concept by putting hot water in contact with cool air. The primary difference is that the air is blown in by a fan at the bottom of the tower rather than using a fan on top to pull air through the tower. The forced draft design was a forerunner to the induced draft. It can be identified by air being blown into the tower from the bottom. The induced draft design has improved performance and less problems in the forced draft, so this design is rarely used any longer. Natural convection cooling towers use natural circulation to provide air. Incoming water is sprayed across the baffles of the tower and cascades to the bottom. As the air inside the tower is heated from the heat transfer, it becomes less dense and rises. As the warm air rises and exits the tower, it draws more cool air in through the bottom of the tower. The result is natural air circulation. Natural circulation cooling towers may have different designs, but all work off the principle of evaporative cooling. Inside the cooling tower is a cold water basin, air inlet, spray nozzles, and drift or mist eliminators. Hot water from the process is sprayed in a mist over baffles. The air below the hot spray absorbs heat from the water and carries away the latent heat of vaporization, removing the sensible heat from the remaining water, causing a temperature drop. The cooled water collects in the basin and returns to the process. The heated air is less dense and rises up the tower, similar to the chimney effect you see in your fireplace. The exit of the hot air from the tower causes cooler air to come in from the bottom and replace it, providing a natural circulation flow through the tower. Natural convection towers have no fans like induced or forced draft towers. Airflow is provided by natural convection circulation. As the heated air becomes less dense and rises, cooler air is drawn into the tower at the bottom.